Okay. Where is this stuff? Okay, so what I want to do today, I want to go through and just take a little time, and we're going to review some stuff, and then probably add some new things to this too. We're going to talk about relations and functions, and this is Unit 2 is I think a lot easier unit. I really do. Unit 2 has to do with linear equations, so equations of lines, and eventually we build up to systems of linear equations. But to me, there's not as many moving parts here. You don't have to remember so many. Like, it's kind of difficult to remember, and you've probably come to terms with this. It's difficult to keep straight all the information about solving an absolute value inequality, for example. Which one is or, which one is and. And you're getting there. I think everybody's getting there. I'm really happy with how we're progressing with this. It's a hard test, but I'll give you multiple retakes. This stuff, I believe, is a little bit simpler. I mean, and it'll be a little more familiar to you. So this will be kind of a catch your breath unit before we jump into quadratics and some other stuff that's a little more difficult. Okay, before we get into the linear part, though, we just have to get our vocabulary straight. We got to understand what we mean when we talk about relations and functions and sort of the anatomy of a function. What does it mean to be a function? How do we represent functions? So this is kind of it's a pretty straightforward, pretty easy stuff. The assignments aren't very hard. There's not a lot of math to do, but it's more vocabulary and concepts. So first of all, a relation is simply just a set of ordered pairs. And it could be an infinite set of ordered pairs, or it could be a finite set of ordered pairs. A relation in math is exactly what it implies. There's a relationship between the input values x and the output values y. Okay, it can be represented in a bunch of ways. We could represent it with a table. And we'll look at examples of all of these. It could be a mapping, or in here we call it a mapping. It could be a graph, or it could even just be a simple equation. Okay, so the set of x values, remember what that's called. If we're talking about a relation or a function, the set of all the x values that we can input into the function starts with a D. Remember what we call that? Domain. Yeah, that's the domain. And so we want to associate that with the input values. You can always think about a relation or a function as being kind of just like a machine. You're going to input some raw materials, and it's going to output the finished product. You're going to input x values, and it's going to output y values. Right? It's going to do something, and then there's going to be some little formula that it follows, and it's going to spit out some y values based on that formula or that rule. So if the x values, the input values are the domain, what are the output y values called? Range. Good. And we got to remember that the range goes with output. How do you keep all that straight? I mean, it's probably not that hard, but here's a little mnemonic device. Helps you remember this stuff. It's alphabetical. X comes before Y, D comes before R, and I comes before O, right? So it's just alphabetically, they're all consistent. So now let's focus on some specific examples of this. Any relation with distinct points, so a finite number, a limited number of points, is called a discrete relation. Discrete, yeah. Discrete means there are distinct, separate values. Okay, so we'll look at some examples. If we're talking about a relation with an infinite number of input and outputs, and when we graph it, it looks like connected lines or smooth curves, we call that a continuous relation. And we'll look at examples of both. So now we know what a relation is. A function is a specific type of relation. It's a special relation that follows this one important rule. The one rule for a function is this. A function, and I'm going to use the fancy math definition first, but then we can distill this down to something that's a lot easier to remember. Thank you. Oh my gosh, look at that stack. How many names are in that stack? Oh man, that's like 8. That's got to be 8. That's crazy. A relation, so our fancy mathematical definition, a relation in which each element of the domain is paired with exactly one element of the range. Okay, if that's true, you can make that easier though. And you've probably heard something like this before. The rule for a function is a relation is a function, and you fill in the blank here. If for each input value there's exactly what? One output value, right? So for each, if we're talking about x's and y's, then for each x value, there's only a single y value. Okay, that's the only rule for it to be a function. So let's look at a couple examples. So here's an example of a function. I'm going to just write a set of ordered pairs here, okay? So what if we had the ordered pair 0, 1, 1, 3, and 2, 5. That's a function, right? For each of the x values, I had 3 x values, 0, 1, and 2, and for each of those x values, there's only a single output y value, okay? Now let's look at an example that is of a relation that is not a function. Maybe we got the point 0, 1, the point 1, 3, and the point 1, 5. Why is that not a function? Where are we breaking the function law here? The 1. Yeah, look what happens here. When x is equal to 1, we get 2 output values. When x is 1, we get output values of 3 and 5. So therefore, it's not a function. Okay? So we can apply, when we're talking about we're talking about discrete graphs. Oops. That's what a discrete graph would look like. Okay, you see, it's just distinctive points. That would correspond, now it's more points than we graphed here, but if I were to graph, for example, this function, right? It's 3 ordered pairs. If I graph an ordered pair in math, what does it represent on the graph? Like if I graph x equals 1, y equals 3, what's the graph of that going to look like? Over 1 and up 3, but what am I going to put there at that place? A dot. Okay, what's our math word for a dot? A point. Yeah, it's a point, right? So each one of these ordered pairs represents a point. The ordered pair is just telling me the location of the point, isn't it? Right? So if I graphed this, I would have 3 points in the xy plane somewhere, right? Well, here's an example of a bigger discrete graph. It's got like 10 points. Okay, but that would just correspond to something like 10 ordered pairs. Now, is this a function or not? Now, you tell me. I'm going to do a little trick here. I'm going to take a vertical line, and I'm just going to drag a vertical line across this thing. And you tell me when I get to a place, maybe you remember this from before, tell me when we get to an important place that disqualifies this.
Stop.
Okay, stop, right? That's the vertical line test, isn't it? The vertical line test just says if I drag a vertical line across a graph, if it intersects the graph in more than one place, then it's not a function, right? Now think why that is. What's the x value here? Looks like it's 1, right?
Yes.
When x equals 1, I get 2 points. What are the ordered pairs of those points? What's the ordered pair of that point right there?
1 and 4.
How about this one right here?
1 and 7.
See the problem. An input value of 1 gave us back 2 output values. And the graphic consequence of that, how does that manifest itself in a graph if we violate the vertical line test like that? It just means that I get 2 points in this case that line up vertically. They have the same x values but different y values. So that fails the test, it's not a function. How about that one?
Oh, I hate this.
There's an infinite number of places where it fails it. Like there's an example of one, right? I get 2 places where the vertical line intersects the function, and so it's not, or intersects the graph, so it's not a function, right? Now this is, see the difference here? This is a continuous graph compared to a discrete graph, right? This has only got a finite number of points. It takes an infinite number of points to draw that graph. Okay? That's not a function because it fails the vertical line test. How about that one? Yeah, we're fine, right? Vertical line only ever intersects that graph in one place at a time, and so that is a function. Okay? So if we want to add something to our notes, then we could say like an example of a function would be something like maybe a parabola, right? An example of a non-function, that could be something like, well, how about a circle? Okay. Question so far. Does that review? That stuff you've all seen at some point before? Okay, good. Okay. Okay, so now let's take these relations and let's extract some information. Like, what if we want to find the domain and the range of each one and then determine if it's a function? Well, what about this example here? What's the domain going to be of this first relation? And I've got my script bracket, so it's just a set of 4 ordered pairs. What's the domain going to be?
-1, 0, 4, and 6.
There you go, -1, 0, 4, and 6. And the rule is when we're writing out a set, using set notation like that, using our script brackets or squiggly brackets, every element of the domain, every element of that set, whether it's a domain or a range or something else, we always want to write those in numerical order. So we can't just go by the order they're listed, we got to actually put them in increasing numerical order. We would not list, like what if we had multiple x values, would we write it twice? No, we don't. We only write each value down one time if it's repeated also. So then what's the range going to be in the correct order?
-9, -5, -2, and 3.
There you go, right, in order. Okay, is it a function?
Absolutely.
Yeah, it is, right? Each x value only shows up once, it only maps to one y value. Oops, didn't want to do that, I wanted to do that. So we can skip down a little bit. Do you see that if we write something in tabular formation like this, it's the same information, it's just presented a little differently. Question?
Does tabular mean like in a table?
Yep, it's a good word. Tabular is an adjective meaning written in a form of a table or something like that. Yep, good word. SAT word. So if we write tables vertically like this is a good way to do it, to write a table, because now I want you to see if I line up if the x column is first and the y column is second, look at that. They just look like ordered pairs then. Okay, so when you have a choice, always write tables vertically. You don't always get that choice, right? I mean, and sometimes you just got to kind of turn it sideways. If the table's written sideways, then the ordered pairs are just lined up vertically instead of nice and horizontal like they should be. But the relationship's still there. So on this one, everybody see that I'm just going to get my domain is just going to be those 4 x values in numerical order, and the range is those 4 y values in numerical order. And, no x values are repeated, so it's a function. Okay, so this is what we call a mapping. Just another way of representing the very same information, right? This time it's not a set, it's not a table. We're using it's kind of like a Venn diagram, right? We're just using these blobs that enclose the domain and another blob that encloses the range. Now what's nice here though, when we use the mapping, we can use arrows to represent where each input lands, right? So in this case, the input -4 gives us the output of 0. When we input the -4 into our machine, relation machine, it spits out a 0. So study that for a second and tell me what you think. Well, first of all, what is the domain of that? Let's write that.
-4, -2, and 5.
Good. -4, -2, and 5. Okay, what's the range? 0, 3, 7, 9. Okay, you got that. Now here's the $1,000,000 question though. Is this a function?
No.
It's not. How come? Why is it not a function?
The domain. The input will have an output.
Okay, good. So the output 5, that's where it breaks down, right? The input value of 5 gives us 2 separate output values. So why is that easy to spot when we're using a mapping? Because we've got 2 arrows leaving from a single input value, a single element of the domain, right? So that's a dead giveaway that that's not a function. Okay, what about, so this is a no. What about this one over here? Domain, would you agree the domain in order is just 2, 8, 13, 17? Range, -4, 0, and 7. Okay, now here's the important question. Is this a function?
Yes.
Okay, it is. Now, even though, how is it a function if I've got 2 arrows pointing at 7? Does that matter? Doesn't matter, right? It doesn't matter. There's nothing wrong with having different input values point at the same output value. That's okay. We just can't have a single input value pointing at more than one output value. right? If I look at the rule here, all we have to ask ourselves is, does each of these input values only pair with one output value? Yeah. If I input a 2, I only get one output, and that's a 7. If I input an 8, I get only one output, that's a 0. Yes, sir.
If there are less domains than, like, range, you know what I'm talking about? So let's say we have 3 numbers up top, 4 numbers on the bottom for range.
Yeah,
It's, like, you can automatically tell it's not
You can.
fine, right?
you're right, you can. And that makes sense, doesn't it? Because then you know that if I've got fewer elements in the domain than there are in the range, then at least one of those has to point to more than one output, right? Has to be the case. Now, okay, that's a good question now. Now think about this carefully. I'll ask you just kind of a logic question here. If I have 10 elements, so if I have 9 elements in the domain and 10 elements in the range, can you tell me, is it guaranteed to be a non-function, guaranteed to be a function, or either way? And you already got the answer to this. What is it?
Guaranteed to not be fine.
Guaranteed to not be a function. Everybody agree with that?
Yeah.
Okay, now, what if I've got 10 input values and 10 output values? Can I tell? I can't. It could be either or, couldn't it? Could be either or, because I could have maybe like 2 input values that point to a single output value and also a single input value that points to 2 output values. I'm still going to end up with 10 and 10, aren't I? But it could go either way, right? And the same thing would be true if I had 10 input values and only 9 output values. We still don't know, right? We still don't know. We could still have a case where we have one input value that's pointing at multiple output values there, right? We couldn't tell. Good question. So this one is okay then, we said, isn't it? Right?
Yeah.
Because each input value only points at one output value. In other words, the arrows leaving the inputs, there's no double arrows leaving the inputs, right? Okay, what about this guy down here, number 7? Now let's be really efficient with this one. It's not a function, first of all. We can see that because I've got these 2 points line up vertically, don't they? So we already know it's not a function. Now what if I want to write the domain here in order? There's a way we could do this. We could be really slick about this and really efficient. What do you think? What's your strategy going to be for writing the domain?
Well, left to right.
Yeah, there you go. So I'm just going to get, that's an x value of -3. That's an x value of 0 scooting to the right. That's 2. And that's 4, right? Now what if I want to write the range in order? Instead of going left to right, I'm going to go,
Right to left.
no.
Yeah.
Okay, but where am I going to start?
From the bottom.
Bottom to top. Good, because the y values are going to start small and get big as we move upwards, right? So the range would be, I'm going to start at -5, and then what have I got? -2, and then -1, and then 1, and then 4. Everybody see that? Okay, no big deal. And it's not a function because it overlaps vertically. Okay, so now what about this guy here? Now we're shifting gears. Right now, for the first time, we're trying to find the domain and the range of something that's not a discrete set. Right? Instead of having a finite number of points or a finite number of inputs and outputs, like all these previous examples, now we've got one where I've got this continuous function. It's a line, simple line, right? So first of all, is it a function?
Yes.
Yes, it is. It passes the vertical line test. Okay, now the domain, I'm going to have to opt for a different strategy here, right? I can't write down individual points because there's an infinite number of points stored in that line. So yeah, so Kyle, what's your thinking here? What is the domain? It's infinity, right? All real numbers will work, won't they? You name a real number, I guarantee if we zoom out enough on this, I can find a point if you name any real number, doesn't matter how big or small, if we zoom out enough, we can point to a point on the line that has that x coordinate, right? The x coordinates of all the points on this line would go from -infinity up to +infinity, so it's all real numbers, right? How about the range?
Well,
Yeah. If we zoom out far enough, we can point to any y value of a point, right? Because if we zoom out far enough, this line goes up forever and down forever. Okay. Okay. So how about Let's look at a couple more specific examples. So how would I write, the domain's obviously -768, right? In this one? Everybody agree? What's the range? 3. That's it. Okay, is this one a function?
Yes.
There it is. Yep, so it is a function. Okay, so what's going to happen, just to reiterate something, if I graph this thing, I've got 3 different input values that happen to point at the same output value. Notice how they line up. You tell me, how are they going to line up? They're going to be flat, horizontally flat, aren't they? Because we've got the same y value but different x values, so they line up horizontally. That's okay, isn't it? That passes the vertical line test. Okay, but if we take a function or a relation like this guy,
Oh, no.
okay, yes or no?
Not a
Function?
function.
Not a function. I got a single input that maps to 3 outputs. How are those points going to line up, do you think? Vertically. It's going to fail the vertical line test, isn't it?
No.
Right? Okay. Okay, so let's look at a couple other examples then. More of these continuous graphs. Now we've kind of shifted gears. We're working on studying these continuous graphs. Domain and range of this function up here. I'll make it blue so it's easier to see. Okay, once again, we can't write this as a set of discrete values because there are an infinite number of values. But could you find a way to describe the infinite set of x values represented in that graph? So the domain is the set of all the input values that are graphed there, all the x values.
But it's not all the x values, is it?
Well, so
You wouldn't hit every x value.
you wouldn't, you're right. So we have to specify which ones are in the domain and which ones aren't. So how could we describe all the x values that are included in the domain? It's not all reals this time, is it?
No.
Say it again. Greater than -4. Okay, anyone want to slightly tweak that? That's a great way to do it. X is greater than -4, but I want to I'm going to say that's 99% right, but there's equal to. See why? Okay, because now think about it this way. I know this sounds kind of hokey, but we even do this in AP Calculus. Talk about ants a lot. If an ant were to crawl along this function, right, what's the furthest left that the ant actually could get? What are the coordinates of the point the ant actually could stand on? -4, -1, right? But it could stand on the x value -4, so that has to be included in the domain, right? Okay, here's a good way to think about this. Now this is never really talked about in textbooks. This is kind of more of something that you do a lot in physics. Like in my physics career in college, we did this kind of thing a lot. It's a simple concept, but it can extend into much more complex areas. We'll do what's called a projection. So if we want to find out what the domain is, we can do a projection of that graph onto the x-axis. Now, what does that mean? A projection. It's a simple concept, but it's very powerful. We could take the function and we could just squeeze all the points. We could just slide all the points vertically onto the x-axis, right? So if we did that, where do we end up? So for example, this point right here is going to slide vertically and end up there, right? This point right here is going to slide vertically and end up right there. When I do the entire graph, what does it look like? It just looks like that, doesn't it? Everybody see that? So you could think about it as sliding or squishing the function onto the x-axis from the top and the bottom. The other way you could think about it is if I shined a light from below and above and cast a shadow on the x-axis, where would the shadow be? Well, the shadow would be there, wouldn't it? Right? Get the idea? So once we graph what the projection is, now we can easily write that as an inequality. What is that inequality? Well, we can see that I've got this closed endpoint that goes to the right. What would just be x is greater than or equal to -4, right? Okay, so what about the range?
That's where things get super easy.
In this case, yeah. If I project this onto the y-axis, how much of the y-axis would it cover? Is there any part of the y-axis that wouldn't be covered? No. It goes forever, doesn't it? Because this function, it's got 2 pieces to it, but it goes up forever if I zoom out, and it goes to the right and down forever if I zoom out. Agreed? So if I project this onto the y-axis, it would literally cover the entire y-axis. And so the range is all reals. Make sense?
Yes.
Okay, is it a function?
No. it doesn't
Nope,
pass for-
it's not, because it fails the vertical line test there, doesn't it? Right? If I drew a vertical line through, like right here, for example, look what happens. We get 2 points of intersection, and so the answer is no. Okay, what about this? Obviously not a function, right? Clearly violates the vertical line test. Okay, see if you can come up with the domain in the range this time. If I project the function onto the x-axis, is it going to have a left endpoint?
Yeah,
Where's it going to be?
-2.
-2. So I'm going to get a closed, because the ant could stand at -2, couldn't it?
Yes.
So I'm going to get a closed endpoint at -2 for my left endpoint. Is there going to be a right endpoint?
Yes.
Where?
5.
5. And then everything in between would be shaded, correct?
Yeah.
So how do I say that interval? That was, we're getting,
Well, it's an and statement.
it's an and statement. Good, so what's that going to be? So x is
Greater than -2.
greater than or equal to -2 and less than or equal to 5. Very good, right? So it's sticking, right? The stuff that we've been talking about, here's an application of that, right? Okay. How about the range? Is there going to be a bottom endpoint on the range?
Yes.
What's it going to be?
-2.
-2. What's the top, is there a top endpoint?
Yes.
Yes. +4. Okay, so now how am I going to say that? Now I'm going to use y is for the domain, right? This is a vertical issue. Okay, what am I going to get? Y is
Greater than
greater than or equal to -2. There we go. And less than or equal to 4. Okay, so once again, this is a good opportunity to go back and kind of just briefly revisit and tie up some loose ends. If I've got an interval that has 2 endpoints like this, that's got to be an and statement, doesn't it? Because it's requiring, each endpoint requires an inequality to create that endpoint. I've got to have, for example, for the blue one, I've got to have the inequality x is greater than or equal to -2 to create that left endpoint. But I also need the inequality x is less than or equal to 5 to create the right endpoint. And this time they both are, because it's one interval with 2 boundaries, it's an and. They both have to be true if I'm going to capture the x values between the lower and the upper boundaries, right? Get the idea? Okay? So what about these guys down here then? So the last type of problem you're going to get on the assignment, you're going to get all these different types, but I'm also going to give you some equations where the graphs aren't provided. How are we going to come up with the domain and the range? Well, there'll be a point later in the year. By the end of the year, you'll be amazed how much stuff you're going to know. By the end of the year, you'd be able to go look at these things and say, okay, just based on what I know those graphs look like, I can tell you what the domain and the range are. We're probably not there yet, right? Especially with the quadratic one. So for now, we're going to rely on technology. And you're going to learn how to use, and this is, once again, this is just such a powerful tool. We're going to learn how to use the Desmos graphing utility. So here's what it looks like.
Yes, Desmos.
And this is a much more souped up and powerful version than the one you've been using. This is when I say a graphing utility, you'll see what I mean.
It's like Desmos on assholes.
This is Desmos on steroids here. This is,
So it's not like crazy powerful, but
it's pretty crazy powerful, yeah. So all you have to do in the Desmos graphing, and I'll embed these in the homework, so you can just click a button and it opens up. In the test, if it's a graphing utility test, I'll embed it in the test. What's nice about this is with Desmos, all I have to do is type in the relation the way it's written. Now, even on like the fancy graphing calculators, like a TI-84 or the TI-89, which we sometimes use in calculus, and it's a super computer algebra system. It does algebra for you, it does all kinds of stuff. You still can't write down a relation that's not a function and expect it to graph it. It won't do it. But in Desmos, you can. So we'll look at some examples of that. In this case, I'm just going to write down the relation y equals -x squared plus 3. And look what it does. It instantaneously gives me a nice color-coded graph. I can graph multiple things at the same time, and I can change the colors if I want to, so they're easy to see. There's so much stuff, and by the end of the year, you're going to be an expert with this. If I want to come up with the domain and the range, well, first of all, is it a function? Clearly, that is a function. If I want to get the domain and the range, let's start with the domain. What's the domain of this function? We now know it's a function. What's the domain of the function going to be? All reals, yeah. Does everybody get that? Even though on the graph it appears to stop, it really doesn't. If I zoom out, it just keeps growing and growing and growing, right? So if I zoom out infinitely far, the function will extend down forever, but also to the left forever and the right forever. Agreed? So the domain, we can say, is definitely all reals. And it is a function. Whoops, it is a function. What about the range? The range was a different story though, right? The range, is there, vertically, is there a lower endpoint on the range? No, there's not. Agreed. There's not a lower endpoint. The function goes down forever. Is there an upper endpoint? There is. This one is easy to see, but in Desmos, it'll always make it easy for you to find. If you click on the function that's being graphed, you notice that it gives you light gray points. It anticipates all of the important points you might be looking for. Why is it giving you these light gray points? If I click on them, they'll show up more brightly and you can see the coordinates. Well, because those are x-intercepts, right? So those might be important for us to find. Why is it showing us this point? Well, really for two reasons. One reason is because it's a y-intercept. But what if I were to do something like, I'm gonna do something like, just for a second here. I'm gonna tweak this thing. I'm gonna slide it to the right by 2. Okay, it's still gonna give me that point. It's changed a little bit, but it still gives me that point because it's the vertex of the parabola, which in this case means it's the maximum. It's the maximum. It's the highest place that an ant could walk on that function. Agreed? Okay? So that's what we're really looking for here. So what is the maximum y value then? What's going to be the upper endpoint of my range? 3. There you go. And I'm going to go from 3 on down, right? So then I would just write my range as y is less than or equal to 3. Get the idea? Okay, good. When are we out of here? 3 minutes. Okay, well, you know what? I'm not even going to go to this stuff. We'll deal with this stuff on Monday.